Today, we're unpacking a hidden, honestly kind of magical force that's behind, well, basically all the technology we use every single day. We're talking about a process called thermal evaporation. You know that anti-reflective coating on your glasses? Or the shiny metallic inside of a potato chip bag? Or, crucially, the impossibly tiny microchips running the exact device you're watching this on? Yeah, thermal evaporation is the invisible architect making all of that possible.
So, here's a wild thought for you. How exactly do you paint something with just a single layer of atoms? Right? Because you obviously can't use a brush, and a spray can is definitely out of the question. When we're manufacturing components that are literally microscopic, we need a way to deposit material that is insanely precise, perfectly flat, and pure right down to the atomic level.
The secret actually lies in a phenomenon you've probably seen a million times: frost forming on a cold window pane. Think about it. When you boil water on the stove, the steam hits the pot lid and turns back into liquid water drops. But in the extreme vacuum environments we use for advanced manufacturing, liquids just can't exist. There's no atmospheric pressure to hold the molecules together. So the material we want to deposit actually sublimates. It goes straight from a solid, vaporizes into a gas, expands outward, and then condenses directly back into a solid right onto our target surface. It completely skips the liquid phase.
To really get how we control this, we're going to systematically break it down. Here's our roadmap for today. 1. The basics of thin films. 2. From light bulbs to telescopes. 3. The physics of evaporation. 4. Inside the vacuum chamber. 5. Film growth and microstructure. And finally, 6. Real-world applications and limits. All right, let's kick things off with Section 1, the basics of thin films. At its core, thermal evaporation is a key technique in a family of processes known as physical vapor deposition, or PVD. And the concept is beautifully simple. We take a solid chunk of material, say a piece of aluminum or gold, and we heat it up inside a high vacuum chamber. We keep heating it until its vapor pressure gets so high that atoms literally just start escaping right off the surface. Those vaporized atoms then fly through the vacuum until they smack into a cooler object, which we call a substrate, where they instantly condense to form an ultra-thin film. Moving right along to Section 2, from light bulbs to telescopes. What's super fascinating here is that this incredible technology actually started out as a totally annoying bug, not a feature. Back in the late 19th century, Thomas Edison and the folks at General Electric were pulling their hair out over a problem called bulb blackening. The filament inside early incandescent light bulbs would slowly evaporate and coat the inside of the glass with this dark soot, which completely ruined the bulb's lifespan. Well, by 1912, scientists Pohl and Pringsheim realized, hey, we can actually harness this effect on purpose. They adapted it into a formal vacuum deposition process, but it really hit its stride in the 1930s when John D. Strong figured out how to use this exact method to coat giant telescope mirrors with aluminum. Aluminum was way too reactive for the old wet chemical baths, but in a vacuum, it created a brilliant, flawlessly uniform glassy coating. It was a real game changer.
Let's transition into Section 3, the physics of evaporation.
So the absolute secret sauce of thermal evaporation is a physics concept called the mean free path. This is simply the distance an atom can travel before it crashes into a random background gas molecule. In normal everyday air, an evaporated atom wouldn't even make it a fraction of a millimeter before slamming into oxygen or nitrogen and totally losing its trajectory. But by pumping the chamber down to a super high vacuum, we're talking 10 to the power of -5 to -7 torr, that mean free path becomes massive, sometimes up to 60 meters long. Since the chamber itself is much smaller than that, those vaporized atoms can travel in straight, ballistic, line-of-sight trajectories directly to the target without hitting a single thing.
And to actually get those atoms to launch off the source material in the first place, we rely on the Hertz-Knudsen equation. Now, without getting bogged down in all the heavy math, the major takeaway is that the evaporation rate is directly tied to vapor pressure and temperature. Every single material has a sweet spot where its vapor pressure becomes significant, usually around 10 to the power of -2 torr. Once you hit that temperature threshold, the evaporation really takes off. Simply put, the hotter you get it, the faster your deposition rate.
Okay, Section 4, inside the vacuum chamber.
Let's peek under the hood at the anatomy of a thermal evaporator. First up, you have the vacuum system itself. This is usually a team effort. Rotary pumps to suck the rough air out, followed by turbomolecular or diffusion pumps to achieve that extreme deep vacuum. Then, down at the bottom, you have the evaporation source. This is often a little metal boat made of tungsten or molybdenum, or maybe a ceramic crucible, which holds your raw material. Up above that sits the substrate holder, which usually rotates to make sure the coating goes on evenly.
But honestly, one of the most incredible pieces of tech in the whole setup is the quartz crystal microbalance, or QCM. This tiny sensor sits right up near the substrate and physically vibrates. As atoms land on it, that tiny bit of added mass changes its vibration frequency. That allows the computer to measure the thickness of the growing film in real time, literally down to the nanometer.
Running this highly advanced machine follows a pretty strict 5-step process. Step 1 is loading, getting your source material and your target substrate securely into the chamber. Step 2 is evacuation, firing up those pumps to suck all the air out. Step 3 is heating. This is often done using resistive heating, where we pass a massive electric current through that tungsten boat until it glows white hot. Or sometimes we use an electron beam fired directly at the material. Step 4 is the main event, deposition, where the vapor travels up and condenses. And finally, step 5 is cooling and carefully venting the chamber back to normal atmospheric pressure. If you skip the cooling and open it too soon, you'd instantly oxidize and ruin your brand new, extremely hot film.
Next up, Section 5. Film growth and microstructure.
So the film actually builds itself atom by atom. It doesn't just splash on all at once like a wet coat of paint. First, the vapor atoms crash into the cool substrate and stick. We call this adsorption. Next comes surface diffusion. These newly landed atoms actually slide and wiggle around on the surface, searching for a stable spot to rest. As they bump into each other during this little atomic dance, they enter step 3, nucleation. They cluster together to form tiny, one-atom thick islands. Finally, as more and more atoms rain down, these little islands grow and merge together. This is step 4, coalescence, which eventually forms a continuous, flawlessly smooth film.
But here's the catch. The final microscopic structure of that film depends heavily on temperature and energy. In thermal evaporation, atoms arrive with relatively low kinetic energy compared to other manufacturing methods. According to something called the structure zone model, if your substrate is too cold, the atoms lose all their energy the second they land and can't diffuse or wiggle around. What you get is a porous film with a columnar grain structure. It looks almost like a dense microscopic forest of stalagmites. It's just wild that by simply tweaking the substrate's temperature, engineers can actually dictate the microscopic morphology and density of the final material.
Which brings us to our final section, number 6, real-world applications and limits.
We've dug deep into the quantum mechanics and the thermodynamics here, but why does all this dense science actually matter to us day to day? Well, it matters because thermal evaporation is absolutely indispensable to modern life. In microelectronics, it's used for metallization, meaning it lays down the microscopic conductive wires inside your smartphone's processor. In display tech, it perfectly deposits the ultra-delicate organic layers inside OLED screens. In optics, it's the process that creates those anti-reflective layers on high-end camera lenses. And on a massive industrial scale, huge roll-to-roll machines use it to coat plastic packaging films with microscopically thin layers of aluminum. That creates a perfect barrier against light and oxygen to keep your food fresh, and it uses a tiny fraction of the metal that a solid foil sheet would need.
Now, thermal evaporation isn't the only game in town. When you stack it up against other methods like sputtering or chemical vapor deposition, or CVD, there are some definite trade-offs. Evaporation is beautifully simple and pure. Plus, because those atoms arrive with low energy, it causes very little damage to highly delicate substrates. But, on the flip side, sputtering uses a high-energy plasma that violently blasts atoms onto the substrate, which actually forces a much stronger adhesion. Meanwhile, CVD relies on reacting chemical gases, which makes it far better at evenly coating highly complex 3D shapes.
And that leads right into thermal evaporation's biggest limitation. Remember earlier when we said the atoms travel in straight ballistic lines? That causes a major issue called the shadowing effect, which leads to poor step coverage. If your substrate has tiny microscopic trenches, walls, or rough textures, the vapor atoms will hit the top ridges but be physically blocked from reaching the valleys below. It's exactly like how standing right behind a tall building blocks the sunlight. Also, it's incredibly difficult to evaporate materials that have extremely high melting points, like tungsten, at least unless you upgrade to a really expensive electron beam system.
But even with those limitations, the ability to cleanly and predictably turn a solid into a vapor and rebuild it, literally atom by atom, is a total cornerstone of modern human engineering. Which leaves us with this final thought. Thermal evaporation was born from the frustrating soot of Thomas Edison's early light bulbs, yet today it physically constructs the very foundations of the digital age. As our microchips keep shrinking, getting closer and closer to the atomic limit, how will this century-old technique, this artificial frost, continue to evolve to help us build the unimaginable devices of tomorrow? Thank you so much for exploring this explainer with me. Keep wondering, keep learning, and I'll catch you next time.